record here. So welcome to the second of our 5 Iowa Nutrient Research Center webinars for spring 2021. And the last couple days, it does feel just a touch more like spring than what it did about a week ago at this time. So for those that don't know me, I'm Matt Helmers, the director of the Iowa Nutrient Research Center. This semester, we're trying to have presentations from kind of around the country talking about different watershed projects or different watershed characteristics. We had Mike Daniels go last month about activities down in Arkansas. We have Jennifer Tank that'll be on in subsequent webinar talking about Indiana, Margaret Kalsick, Ohio, and Jason Hubbard, some of the work in West Virginia. But this month, we are very fortunate to cross the Missouri River, and we have Dr. Aaron Mittelstet from Biological Systems Engineering at the University of Nebraska-Lincoln join us today. Dr. Mittelstet is assistant professor in the BSE department. He started there in January 2016, teaches courses within BSE and advises undergraduate, graduate, and PhD students. Publishes several papers and has numerous grants, and he's going to talk about a couple of the different projects he's been working on. And his interests are in the areas of watershed modeling, surface groundwater interaction, water quality, and stream bank erosion. With that, I will turn it over to Dr. Aaron Mittelstet. If you have questions, feel free to type them in the chat box, or actually Dr. Mittelstet said you can ask them even as he goes through this, because he may talk about a couple different projects. So welcome, Aaron, and look forward to the presentation today.
All right, thanks, Matt. So first off, thanks for the invitation. I'm happy to present to you guys today. And one thing, I'm talking about 4 to 5 different projects. So anytime throughout the presentation, if you have questions, feel free to just put it in the chat box or unmute yourself. And also, one thing I like at the end of the presentation is my email address. I know there's a lot of good work that comes out of Iowa and Iowa State on water quality and stream bank erosion. And I would really like to increase the collaborations between my department, myself, and my colleagues in the faculty in Iowa. So if you'd like to collaborate in the future on any projects or grants, feel free to contact me. So with that, I'll get started. So as we know, nitrogen is a major concern globally. This graph kind of shows the large increase in nitrogen fertilizer use since the 1960s. And as the concentration of nitrate, when it exceeds 10 milligrams per liter, can cause issues like blue baby syndrome. And then a recent study in Rhodes, I think 2013, found that nitrates that exceeded 2 milligrams per liter in combination with atrazine can increase the chances of getting non-Hodgkin's lymphoma. So, and then you can also get other cancers as well. It's increased the treatment cost, and of course can cause eutrophication and algal blooms. So a few years ago, shortly after I got here, the Department of Environmental Quality, their new name is now Department of the Environment and Energy, they gave us a data set, 17,000 samples that they collected from 2002 to 2014 at 84 sites across Nebraska. So we kind of brainstormed what we wanted to do with this nice data set. So most of these samples were taken baseflow conditions and monthly. So here's just kind of a snapshot of the distribution and the concentrations of the nitrate across Nebraska. So right here, the I don't know how many of you been to Nebraska, but this is the green part. This is the Loup River Basin, where the Nebraska Sandhills is located. This is mainly rangeland with cattle. This here is Cherry County. There's more cattle than people, very sparsely populated. If you ever see a picture of cell phone coverage, this part of the U.S. is pretty much like a black hole. You don't get any coverage out here. Here on the here's the North Platte right here, and the South Platte. You can see the North Platte has high concentrations around 3 to 5 milligrams per liter. And then a lot of the high concentrations of nitrate are in the eastern part of the state, which we hypothesize is from all the corn, soybeans, and the high precipitation. So soybeans and corn are grown predominantly in the east, and then out west we have more wheat, and then there's a lot of sugar beets grown in the western part of Nebraska. So the first thing we did is we just wanted to develop a simple regression model to see how well the data fit and looking at different characteristics. So we first eliminated some sites. We wanted at least 50% of the watersheds to be in Nebraska. And then we wanted to eliminate any nested watersheds. So we ended up having 47 watersheds. Then we used 14 variables, basically point sources, different land use, precipitation, baseflow index, and soil properties. We wanted these each of these variables to be freely available and accessible, so other researchers could duplicate our study if they want to. So we have point sources, then different land uses. So in Nebraska, 54% is grassland. This is where all the cattle are located. And then the eastern part and southern part is where most of the cropland is. We have some major point sources across the state. Then developed, here we have Omaha and then Lincoln. So 6 of the predictors were from land use. We looked at the percent developed, the grassland, cropland, and specifically corn, then forest and pasture hay. And then unlike Iowa, Nebraska does have a large gradient in precipitation. The western part of the state having only around 300 millimeters per year, and then the southeastern part exceeding 800 millimeters. So we looked at the average annual precipitation, and then also the average annual precipitation during the growing season from May to September. Okay, they looked at baseflow index. Baseflow index is the percentage of stream flow that originates from the groundwater. Typically, the higher baseflow indexes are in the western part of the state, and then the southeastern part has a lower baseflow index. Then soil properties, we looked at the poorly drained, well-drained, and excessively drained soils, then also the K factor. So these 47 sites, they ranged in area from 6 to over 7,500 square kilometers. And the nitrate concentrations range from 0.17 all the way up to 15 milligrams per liter. So we kind of divided out into 3 data sets. First data set had all 47 sites. Then we looked at just the smaller watersheds, which were those less than 1,000 square kilometers. Then we looked at the larger watersheds greater than 1,000 square kilometers. So just looking at the selected model, we're looking at all 47 sites. We had 5 predictors. This had the best, highest R squared and adjusted R squared. And those 5 predictors were crops, precipitation, point sources, the baseflow index, and then the percent that's excessively drained. Then we look at the just the watersheds greater than 1,000 square kilometers. The R squared and adjusted R squared were much better, 0.84 and 0.77. And we had 4 predictors for these: percent grassland, percent excessively drained, point sources, and then the baseflow index. And then the correlation was not as good for the smaller watersheds. There were really only 2 predictors for this category: precipitation during the growing season, and then the percent of the watershed that is planted in corn. So some conclusions from this kind of first part. So basically we found out that, like we hypothesized, corn and precipitation were the most significant predictors for nitrate. The soil properties also were important predictors for the large watersheds. And we think we could use these simple correlations to kind of get an idea of what nitrate concentrations would be in ungauged Nebraska surface waters. So from there, what we wanted to do is see if we could use these watershed characteristics to help identify the BMPs that we should implement in each of these basins. So we first limited the number of watersheds to those streams that had nitrate exceeding 2 milligrams per liter. And then when we looked at the BMPs, we looked at both the literature, and then we used a field scale model to simulate the impact of the BMPs, kind of look at what reductions we would expect from each of those. So what we did is took all of the characteristics for each of these sites. There ended up being 17 sites that had nitrate exceeding 2 milligrams per liter. And we did a principal component analysis so we can kind of see what groups we had and how many groups we had. Then when we did our simulations, we looked at kind of 3 classifications. We had low leaching, high runoff, and then we had medium leaching, medium runoff. Then group C would be high leaching, low runoff. And then we simulated these BMPs with T-bet. So what is T-bet? I don't know if anybody's heard of this. This was originally called PPM Plus. This was developed at Oklahoma State University. At Oklahoma State, I work with Dan Storm. Some of you may know him. And his PhD student, Mike White. I was working on my master's when Mike was defending his dissertation. He developed this tool, and Mike White since moved to Texas and is working down at Temple for ARS. And so they improved on the tool and changed the name to Texas Best Management Evaluation Tool. So right now, this is set up for Texas, Oklahoma, and Arkansas, and it's something I like to set up for Nebraska. So this is a simple user interface that the objective is to put it in the hands of the producers and the watershed managers, where you can train somebody in 4 to 8 hours just at a workshop on how to use this tool. And they use this, all they see is this simple interface, but it uses the SWOT model. It runs the SWOT model in the background. And it's basically running the SWOT on a field scale. So just a quick little rundown on how this works. They enter the basic information, the location of the county and the ecoregion, and it has the database for the average precipitation and temperature for that watershed. Then you enter the size of your field in acres, the distance to the stream, and then the percentage of your field that's bare soil. And then there's a Surgo database, so you can select a single soil or multiple soils. And then you put in your soil test phosphorus. If you don't know what your soil test phosphorus is, you can click on this button here and answer some questions about management of your field, and it'll estimate what a soil test phosphorus will be. Then there's about 100 different cropping systems: corn rotation, corn, soybean, cotton, wheat, just lots of different options. And then if you do grazing, you put in the grazing rates, irrigation. Then down here for fertilizer, you can do split fertilizer, you can do commercial, you can do manure and poultry litter. So lots of options. So once you do that, you run the model. It takes about 10 seconds, 30 seconds to run it. And it'll give you the average sediment, phosphorus, and nitrogen loss from your field. So then what you can go in and do is simulate all of these BMPs. So you select one, for example, if you select wetlands, you can determine what percentage of your runoff from your field is going to go through the wetland. You're going to have 30% go through or 100%. And then you can run the model again. You can see what kind of reduction you get. So you can also set it up right here. We can have a pre-program as your baseline. And then in year 1, you can select that. Then you can implement a BMP. Then year 2, you can implement another BMP, and you can run all 3 at once. You can really see how your sediment and nitrogen, phosphorus is impacted by each of these BMPs. So that way the producers kind of have more power in what they're wanting to implement, and also kind of looked at the cost effectiveness of each one. So the BMPs we simulated, we looked at split fertilizer application, terraces, no-till, wetlands, cover crops, and then riparian buffers. So here's the 17 sites that had nitrate exceeding 2 milligrams per liter. One thing that jumps out at you is they're all in eastern Nebraska, except for the Frenchman Creek over here in southwestern Nebraska. So several of these have nitrate exceeding 5 milligrams per liter. All right, so when we did our principal component analysis, basically divided everything up into 5 groups. This first group here, sites 3, 6, and 47, were herbaceous, the high baseflow index, low runoff. So we're going to expect a lot of nitrate leaching in those watersheds. Group 2 here, site 8 and 33, it's predominantly cropland, excessively drained. So also we'd expect a lot of the nitrate to be lost through leaching. Group 3 was the largest group, had higher slopes, mainly cropland, corn, and a lot of precipitation. And with this one, it's mainly based on the soil characteristics. It's going to be high runoff, so we expect the nitrate to be lost through runoff. Group 4 here is developed. One of these is in Lincoln, and the other one's in Omaha. So we expect high runoff, and the nitrate would be lost through the runoff. And then site 26 here is by itself here. It's dominated by a point source. Then we had one site 10, that really didn't fit into any of the categories. So here's the sites here. So group 1, we have this watershed out in the southwestern part of the state, and then we have these 2 small watersheds in the north. Group 2, we have these 2 lilac ones here, and then group 3, you can see they're all grouped together in the same precipitation location. And then we have our 2 urban watersheds right here in the southeastern part of the state. All right, so what we did is groups 1 and 2, we set up a baseline scenario where we use just typical characteristics of a field in eastern Nebraska. And then all we changed was the soil type. So to simulate groups 1 and 2, we used a fine sandy loam, which would represent well-drained soils. Group 3, we used silt loam, which would represent medium runoff. And then group 4, we used the silty clay loam, which would represent high runoff. So what we end up finding is when we find with the T-bet simulations, the fine sandy loam, as predicted, we got lost a lot of nitrate through leaching. And the biggest reduction was from split fertilizer and then from cover crops. So those were the most effective at reducing nitrate leaching. Then we go over to the silt loam and silted clay loam, kind of similar results. There wasn't any nitrate loss through leaching, but most of it was from runoff. And the biggest reduction was from the wetlands, and then the split fertilizer application, and then the riparian buffers. So those were the most efficient at decreasing the nitrate. So if we make some recommendations, group 1 and 2, split fertilizer application, cover crops, and one thing that T-bet does not simulate, but could be implemented in those watersheds with high leaching would be to credit the nitrate in your irrigation water. And we do have some faculty here that are working with producers to try to get them to account for that nitrate in the irrigation water. But there are complications, and because farmer never knows if the nitrate concentration is going to be consistent. And, for those years we get a lot of rain and they don't irrigate, then they're going to have to add commercial fertilizer. So definitely some things to work out, but hopefully we can improve in that area. So groups 3 and 4, where they lose most of their nitrate through runoff, we recommend the split fertilizer application, the wetlands, and the riparian buffers. So the last step we did in this little project was to identify the 10 creeks that contributed the most largest load of nitrate. So we could really help decrease the amount of nitrate reaching the Missouri and Mississippi rivers. So then we used what we learned to kind of identify some BMPs that we would recommend. So a lot of these were the nitrates lost through surface runoff. So for those, we recommended the fertilizer management, wetlands, and riparian buffer. Pepion Creek and Antelope Creek are the urban watersheds. We recommend the bioretention cells, retention ponds, and other BMPs. And then this on North Fork Elkhorn is some sandy soils, a lot of leaching. So we recommend the fertilizer management, the cover crops, and then the nitrate credit and irrigation. So this paper was published 2 years ago in Ag Ecosystem and Environment. All right, so another project, the DQ also gave us a lot of atrazine data. So we had 68 sites where we had both atrazine and nitrate data. So just a couple slides on what we did with this project. We basically calculated a risk factor for those sites. So as I said before, 10 milligrams per liter is usually what the water quality standard is for nitrate. But if you get 2 milligrams per liter and atrazine, that combination can increase the chances of some cancers. So first thing we did, and this formula does not look right. I don't know if it's because I'm on a Mac now. But anyways, we calculated the risk factor for a 90th percentile. And I won't go into the details since you can't really see the equation. So first we did risk factor for the drinking water standards. So 3 micrograms per liter for atrazine and 10 milligrams per liter for nitrate. So as you can see, we did this from 2004 to 2014, but I'm just showing you the 2009 to 2014 here. In the eastern, southeastern part of the state, we're at high risk for atrazine. The concentrations are very high. You can see in 2011, that was a drought year. The risk was much lower. Then if you look at nitrate, it's pretty much low risk everywhere except for this is the Woods River where that point source is located, and the concentration there is about 15 milligrams per liter. So then next we look at the dual risk factor. So first on the left here is looking at if we have atrazine and nitrate at 10 milligrams per liter. But then the right one is if you look at have nitrate at 2 milligrams per liter and then atrazine as well. And as you can see, there's a lot of hot spots here. And most of eastern, southeastern Nebraska is medium risk to very high risk in the surface waters. And then most of western Nebraska is very low risk. So this paper was published just 2 years ago as well in Journal of Environmental Management. It's been well received. I believe it already has 18 citations. So now we're going to zoom into a specific area in northeast Nebraska. This is the Brazil Groundwater Management Area. You can see the location right up here, location of the Brazil Creek Watershed. And they started noticing high concentrations of nitrate in both the groundwater and the surface water back in the 80s. This is an EPA, well, the management area was formed in 2016, and it's an EPA Section 319 area. So they do receive funds for the non-point source. So there's a lot of money going into this watershed. All right, so here's the watershed right here. You can see the northern part. One thing that's unusual about this watershed is it actually flows north. So here's the headwaters here, and it flows north, and then up here it'll empty into the Missouri River. The north part of the watershed is mainly pasture and forest, and then the southern part is mainly cropland, predominantly corn and soybeans. So 60% of the watershed is cropland and 35% is pasture. So in the literature, there's lacking in the literature studies where they really did an intense sampling campaign and sample not just the main stream, but also the tributaries. So what we really wanted to do is see the variability of nitrate in both Brazil Creek and several of its tributaries. So we sampled monthly nitrate at multiple locations. There was one USGS gauge station towards the outlet center, but we also wanted the discharge upstream of there. So we installed 2 transducers, and we did do a couple of flow measurements, but as you may know, it's challenging to develop a rating curve. So based on those flow tracker measurements, we kind of calculated a Manning's N, and then use that Manning's N to kind of get an estimate of discharge for the remainder of the data set. And then what we want to do is once we had that variability of nitrate, we wanted to see if we could explain that variability based on the land use, the soils, and the groundwater nitrate. And then we also looked at the groundwater age, which I'll discuss later. So we sampled, this is Galen Richards, he's the PhD student that worked on this, co-advised by myself and Troy Gilmore. We sampled from July 2018 to September 2019. We had 9 sites. We had 3 on the main channel. So center is right up here. Then we had 3 on Brazil Creek. Then we had sampled 6 tributaries. So this tributary right here, tributary 5, we're going to be doing some future work on that this summer with the ARS. We're going to install 2 transducers, 1 upstream, downstream, and then some POSES. A POSES is if you have never heard of it, it has a filter in it, and you set it out for a month at a time, and it basically collects those pesticides throughout the entire month. So instead of going out, because testing for pesticides is quite costly, so instead of going out, and getting several samples throughout the month, you basically get a cumulative pesticides for each month through the year. So we're going to be doing that project later on this summer. And really the objective there is we're looking at some pesticides that haven't been used and applied for several years, but this stream right here is basically really has a high baseflow index. We're going to see how, if those pesticides are still in the aquifer and still being discharged into the stream. So then you can see our 2 transducers right here, one right here and then here. So one thing you'll notice about this data, the nitrate was highest in the wintertime. So unlike most sites where you get the highest nitrate when you have a lot of runoff, it's the opposite here because at Baseflow, that's when you get the highest nitrate. And whenever it rains, you get runoff that actually dilutes the nitrate in the stream. So the groundwater nitrate is so high that the surface water is lower compared to the groundwater nitrate. You kind of see the each one follows the same pattern where you get the highest nitrate in the winter and the lowest in the spring, and then increases a little bit in the summer and then in the fall. So looking at the variability between sites, so if you just went out to Brazil Creek itself and took samples, that's about 10 milligrams per liter. And if you assume the entire watershed was like that, then you would be wrong. So 2 of these other tributaries, SWT1, SWT5, exceeded 15 milligrams per liter on average. And then 2 sites, SWT2 and SWT6, were quite low with an average of only about 3 milligrams per liter. So then the question is why the variability? So first step, we just kind of looked at a simple correlation between the watershed land use and the nitrate concentration. And we did have this one little outlier, SWT2, which I'll talk about in a second. But overall, there's a strong correlation between the land use, the percentage of the watershed that's corn, and the nitrate concentration. So then what we also looked at all the wells that were sampled in since 2010. It looked at the average. And one thing you'll notice, the outlier, SWT2, is right here. That has the lowest groundwater nitrate of about 5 to 10 milligrams per liter. And what we also noticed when we were out there, we did falling head tests so we could kind of see the connectivity between the aquifer and the stream. And this watershed right here was also, the stream was had a lot of clay. So there was not a lot of interaction between the stream and groundwater. So it's mainly surface water in the stream. So that's another reason why the nitrate's so much lower. And then these other areas with high nitrate, they both have a lot of high nitrate in the groundwater that's feeding the stream. And then also they also had the falling head test showed that there's a strong connection between the stream and the groundwater. So overall, these were sites were explained fairly well with the groundwater concentrations. So I'm sure you guys remember in 2019, we had that huge flood. I'm not sure how much Iowa was affected. So this was our picture of our site on normal conditions, and this is the flooding conditions. I'm not sure if this is the peak flooding or not, but we had a landowner take this picture for us. We have another student is kind of evaluating the significance of the flood across Nebraska, and they calculated this as a 260-year-old flood. So one thing, this large flood could have influenced our results. So we would like to continue sampling in the future if we can obtain more funds. All right, so some conclusions from this project. As discharge increased, the nitrate concentration decreased, which is opposite of a lot of study areas. The nitrate concentrations were quite variable among the tributaries, and most of that can be explained by the percentage of corn in the watershed and then the groundwater nitrate concentrations. And this paper was also published in Ag Ecosystem Environment and just was published this year. Okay, so I'm not sure how many people are familiar with groundwater age and legacy nitrate. This is kind of a new area for me. Troy Gilmore, one of my colleagues, he worked a lot of this in when he's in North Carolina. So when we implement best management practices, a lot of times we want to see immediate results. So as you know, if you implement BMPs this year and this next year we have a drought year, then we may see significant improvements just because of the weather. But the opposite could happen is we have a lot of precipitation the following year and we see worst, we see more sediment, more nitrate, more phosphorus, and then it's like, oh, the BMPs didn't work. So of course, there's that to consider when looking at the impact of BMPs. But another thing to consider is the legacy nitrate. So when we look at groundwater age, the water travels through the vadose zone, and when it reaches the water table, that's basically day 0. And then the water travels through the aquifer and then will discharge to the stream. So what we do is we'll put a piezometer 30 centimeters to 50 centimeters into the stream bed and take a sample. So basically capture that groundwater before it enters the stream bed. And as you imagine, you're going to get a distribution, large distribution of groundwater ages. So if the water infiltrates near the stream, it's going to be much younger groundwater than if you have water infiltrate way out here in the headwaters. It's going to travel and take a long time to get through this aquifer and reach the outlet. So the implications for this is if the average groundwater age is 30 years, whatever we do now, we're not going to see any impacts from that for 30 years. And that's something that's important for people to realize because you could seize, and we have some preliminary results on Brazil Creek. It's not published yet. We're going to do some more work this summer that the age is around 20 to 30 years. So they want the water quality improved now, but there's so much nitrate in the groundwater that it just is not going to happen no matter what they do right now. So when we do the groundwater age dating, we use tritium helium. That's typically for, if you want to look at the ages of less than 100 years. You can also use SF6. Then when you're looking at the 100 to 1,000 years, used argon. Troy and I just built a degassing unit so we can actually sample for argon. And then when you're looking at the older water, you're looking at krypton 81 and carbon 14. And over in the Sandhills, we have an NSF grant where we're doing a lot of age dating there. And if anybody hasn't been to the Sandhills and you'd like to visit, we have a place at Bert Gedmonson. It's like $30 to stay there. It's really cheap. It has a dorm, kitchen, and it's just a beautiful area. But the water there, we sampled the water you get from at the dorm comes from a 600-foot well, and we sampled that, and it was 500,000 years old. So we're wanting to put up a sign saying you are drinking water that's 500,000 years old. So what do these distributions look like? So this is from the Sandhills project that we're working on, but we look at the headwaters, 13,000 kilometers, 20,000 kilometers. So 50% of the water is 30 years or younger. And then for these headwaters, 100% of the water is less than 100 years old. But then you get out here towards the outlet of the watershed, only 30% of the water is less than 100 years old. So 70% of that water in the coming out of the stream bed is older than 100 years old, and some of it's 10,000 years old. So this is from Tesorero et al. 2013. And one thing this is kind of showing is to kind of give you an idea of based on your Baseflow index and nitrate, how vulnerable your site would be to this legacy nitrate. And basically he uses 0.4 Baseflow index of 0.4. So basically 40% of that water in the stream is going to be coming from the groundwater. So if you have that and the high nitrate, there's a good chance that you're going to have to deal with this legacy nitrate. And of course, you can see Brazil Creek in northeastern Nebraska, and then a lot of Iowa here is in that area. So there's a good chance in these areas that no matter what we do right now, as far as BMPs goes, we're not going to see any significant changes in water quality for 10, 20, 30 years. So, and with that, I'll be happy to answer questions on any of these projects.
Thanks so much, Aaron. We have time for questions, and we have a couple questions in there. So the TBET tool, I was not as familiar, so I'm gonna have to go look into that a little bit. But so was that developed for Texas, but then looks like you've gotten pretty good use of it in Nebraska. Do you think it would be relevant in Iowa?
Yeah, it would. So it hasn't been the databases haven't been updated for Nebraska,
Okay.
but I know how to do that myself. But yeah, I think it'd be relevant for any place, and it's pretty, like I said, simple to use. I have some of the trainings. I've given several trainings on this. I went to Georgia and gave a training. You can train somebody in 4 hours to use it. And it, of course, there's a lot of uncertainty in these simulations with any model. It does give you a good estimate of what kind of reductions you can expect.
Somebody kind of asked about that, and I'd just share that there's also the nutrient tracking tool that some folks are starting to use in the upper Midwest as well.
Yeah, I know in here in Iowa, you guys have that. I always show my 354 class. I forget what it's called, but you calculate the erosion.
Oh yeah, the one that the soil loss calculator, right. I think that DNR uses. Yep.
I think it uses WEP.
Yep. Oh, and we also have the Iowa Daily Erosion Project as well.
Right. Yeah, that's a pretty cool project. And I know they've started to do the same thing in eastern Nebraska as well. Yeah.
So there's one here that I think this discussion on lag time and the time, dating of the water so important. And so somebody asked, is there any shorter term strategy we can use now to mitigate nitrate instead of waiting 30 years for results? And I think, well, I'll let you answer that. To me, that's one of the challenges. If it's in that water, in that groundwater that's just slowly moving toward the stream, where we are very challenged.
Yeah, that's a good question. I mean, also you have to consider the nitrate in the Betel zone. That hasn't even gotten to the aquifer yet, and the Betel zone may only take days, but that could also take months or years, depending on the depth of the Betel zone. I mean, I don't really know. I think using the groundwater for irrigation, when you account for that nitrate, that would help a little bit. But really, I don't have any easy solutions on that. I mean, that's one of the issues that other people here, they want some to improve the water quality, and they keep throwing a lot of money at Brazil Creek, but they don't really understand. That's one reason why we did this project, because they don't really understand that no matter what we do right now, we're not going to see any significant improvements.
Yeah, there's still importance to do it for the future, but right. for the next short period, we may be challenged.
But if you tell producers, some of them will be like, okay, that's great, for my kids, their kids, but others will be like, maybe more like, well, if I'm not going to see any changes in my lifetime, what's the point? Yeah. So it's a really touchy subject.
Yeah. So there's a question here. The split fertilizer application appears to be one of the most effective practices, even better than cover crops. I guess the question was that transport mostly nitrogen runoff? And I guess, how much work has been done on cover crops to evaluate their effectiveness in Nebraska?
For nitrate, I don't think there's been a lot of studies, and it's pretty tricky actually, because cover crops in the literature, I kind of see mixed results on how effective they are at reducing nitrate. With riparian buffers, pretty much they all say, oh, it helps nitrate and reduces it. But cover crops have been kind of opposite. We had a project where we used the SWAT model in the Big Sandy Creek, And we were going to look at cover crops as one of the BMPs that we implemented, but we got really weird results. So I really don't think there's any, with the SWAT model, there could be a lot of improvements, and I think we need more studies to see how effective cover crops, and there's lots of different kinds of cover crops too, and how effective are they at actually reducing nitrate.
When you're thinking of the split application BMP, was there kind of, what were you thinking of the timing and maybe rates of that split application for that type of scenario?
Right. So instead of applying it all at once, you would apply 2 to 3 times. I think in my simulation I just did two applications, but I know if you do 3 or 4, that's definitely would be better. But it's also increased the cost of fuel and everything. So it's easy sometimes for us to say, oh yeah, you should apply nitrate 3 or 4 times a year, but then also for a farmer, it's not. There's challenges with that as well.
So there kind of a specific question here on the acid preservation you use for samples for the nitrate.
Right. Yeah, right here.
Yeah. Okay, yeah, they wondered if it was sulfuric acid, hydrochloric acid.
Yeah, I'm pretty sure he used sulfuric acid. He worked with Dan Snow. I think of all you probably know Dan Snow. He's the one that runs the water quality lab. But I'm pretty sure it's sulfuric acid. Or honestly, I don't know. But whatever Dan recommended.
Yeah. So we could find that you could find UNL Water Sciences Lab, the protocol there. So this is really interesting on kind of when we think about the nitrate and that atrazine. And are you familiar with any other pesticides besides atrazine that have similar interactions with nitrate, or that you or anybody else at Nebraska is investigating?
No, that's something Tiffany and I had talked about investigating. I mean, we did a recent study where we looked at, we used those poses to look at the amount of pesticides flowing into 3 lakes around Lincoln, basically an urban dominated one, one that's mainly grassland, and one that's cropland. And the urban had the most pesticides. And it would depend on what pesticide you looked at, but that's was published in Environmental Pollution just this year. But then that's a whole nother question, is once you have these pesticides, when you start mixing them with not just nitrate, but with other pesticides, and then you have they degrade into something else that may be even worse. I mean, it's kind of scary, all the different things we have in our water, and it's really complicated to really see, how they all work together and can affect each other. So yeah, there's a lot of work to go into this area.
I think we have time. If anybody would like to unmute and ask Aaron a question, we can certainly do that as well. So I don't know if anybody would like to unmute and ask, rather than y'all might be tired of hearing my voice. There is one more that I guess this individual indicated they would have expected that the nitrate concentrations in groundwater older than 100 years might have been quite low, or low. And doesn't the impact of high nitrate and BMPs relate mostly to young groundwater?
Right. So the one I showed you where the water was like 1,000 years old, that's in the sand hills where the water is very clean. We're looking at a whole nother, that has nothing to do with nitrate at all. And sand hills water quality is not an issue. Bazille Creek, most of the water is mainly 10 to 30 years old. But you're right that we wouldn't expect, if the water is 1,000 years old, that wouldn't have any influence at all, because we didn't start a lot of application of nitrate till the 60s. So if it's older than that, it's probably gonna not really impact the stream water.
Okay. I guess this is kind of two ask the same question. Are there what are the next steps for your watershed research, and if there's some important areas that you see are not currently being investigated that you would like to in the future?
So one thing I'm working on right now is, and I think it's probably an issue also in Iowa, is the red cedar. And we're really looking at the encroachment of the red cedar and the Nebraska sandhills and seeing what impact, because red cedar has a much higher ET than the native grassland. So we're seeing what impact that's going to have on the hydrology. And yeah, we found that does have a significant impact on the stream flow and the recharge. And then that Loop River, that flows into the Platte River. So if we get a reduction in flow from the clean Loop River water into the Platte River, then the water quality in the Platte River actually will decline. And then that then will flows into the Missouri River, and um, both Omaha and Lincoln get their water from the Platte River, so that can increase our costs. Another thing we're looking at is whenever people model the groundwater age and then they collect samples of groundwater age, they don't really match up. So the NSF grant, Troy Gilmore's kind of the lead on that, but we are taking all these samples to see what the groundwater age is. Then we're using ModFlow to simulate that. And we're seeing how well they compare and where they don't compare at, and why does the model not simulate the groundwater age accurately. And so that's another project we're working on. And we just got funded recently with the floating treatment wetlands. There haven't been any floating treatment wetlands in Nebraska. Most of them have been down in North Carolina, down south. We just put a floating treatment wetland in a water body last summer. And we're going to see how it responds a year or two after the cold winter. But we got funding to install 3 more floating treatment wetlands at 3 other water bodies, and kind of see what impact that has on the nitrate in each of those water bodies. And hopefully if it works well, then we can start incorporating those more in this part of the country. So
I think there was a point there. Yeah. Okay. Kind of 2 questions on this. If you can describe a little bit more the floating treatment wetland.
So Tiffany Messer and I, and I don't know if you guys know Steve Comfort, we're working on this one together. But there's basically these mats that you put a hole in, and then these mats float, and they kind of like a puzzle. You can connect them to make the floating treatment wetland as large as you want. And typically, you want it to be around 2 to 8% of the area of the water body. And then what you do is you make these holes, and then you put these different plants, brush, cattails, different things inside those holes. And then throughout the year, they'll get big, larger, and then they'll remove the nitrate from the water. And then, and this is more Tiffany's area, but then a lot of what we get released is gas. And we have a student working on this right now, so we're going to be getting preliminary results later this year. But overall, we are seeing improvements in the water quality from that. And in that same system, we're injecting lanthanum, and lanthanum is kind of like it basically will bind to the phosphorus, and then it'll settle down to the bottom. So the lanthanum will help reduce the phosphorus in the water column, and then the wetland hopefully will reduce the nitrate. So that's the goal.
Another question here. If you looked at can you speak to studies in Nebraska about legacy phosphorus and eroded bank material? Do you know of any stream bank stabilization structures or projects focusing on limiting P inputs?
No, I mean, in Oklahoma, I did have a project like that where we looked at the phosphorus in the stream banks. And we did find that the phosphorus in stream banks was quite high and can be a significant contributor to the phosphorus load. Here in Nebraska, most of my work has been done on Cedar River, where they had 24 stream banks stabilized back in around 2004. We went back to each of those sites to see the impact and see how many of those stabilized banks are still stabilized. I mean, they were stabilized with jetties, rock toes, rock veins, and seeing how many are still intact, how functional they are, and then looking to see how effective they were. So we're really going in and seeing what the erosion was back in 2000, see 1995 to 2004 before they were put in, and seeing from 2004 to 2018 to see how effective each of those were. And then we also not just looking at the site where the bank was stabilized, but we're also looking at upstream and downstream. But that's one thing that's often ignored is what influence, once you stabilize a bank, do you increase the erosion downstream? Because you know that water still has that energy, and if it's not dissipated, you may get more erosion just downstream of that. But that's one thing we have not looked at, though, is the how much phosphorus and nitrogen is in those banks, and how much that would contribute downstream. And this site's more in the sandhills, so I wouldn't expect it would be too high.
I just, in case somebody's interested, Keith Schilling and some others just had a paper published in the Journal of American Water Resources Association looking at kind of the extent of stream bank erosion in Iowa. So more Iowa related, but Keith and others are doing a lot of work on that, and Tom Eisenhart as well, and John Kovar and National Lab for Ag and the Environment, ARS, specifically on phosphorus there. So put it out there again. If anybody has any other questions for Aaron.
I was gonna say, I've read a lot of their papers, and a lot of good work coming out of Iowa. I would love to collaborate more with Keith and some of the other folks.
Great. Maybe you can put up your last slide with your contact information in case somebody has a follow-up question they might ask, if that's okay.
Yeah.
Okay. And with that, if you can all virtually, and if we were in person, we could all round of applause for Aaron, but virtually thank Aaron for the presentation. I think this is really interesting, gives us lots of things to think about, and I'm certainly with you, Aaron. I hope there's opportunities for those of us in Iowa to collaborate with you at Nebraska in the future, you and your colleagues at Nebraska in the future. There are a number of people from Iowa State that are now over there, and hopefully we can develop some good research collaborative relationships into the future.
Yep, sounds good.
Okay,
It's been a pleasure.
Thanks a lot. You bet, thanks a lot.
All right, bye-bye.
Yep.